fast forward through the bad humor on that one, I'm assuming.
I went through some of it. I didn't watch all of it.
Yeah.
I didn't need to watch all of it. But
Yeah.
I think what is it, 15 minutes long?
Yeah, that's right.
So
Yeah.
I watched probably consecutively 8 minutes.
Yeah, and you can go through and you can it's up on YouTube just like any other YouTube video, and you can go through and pick out those parts that you specifically want to be refreshed on or updated on, so you don't have to watch the whole 15 minutes. Okay, and I've got them down now where they are about 15 minutes. If I get a chance, I'm going to chunk them out a little bit further. Maybe into, they say that you shouldn't go more than 7 minutes in an individual module, but I'm like, well, you can just fast forward anything that isn't of interest to you. So here we go. Okay, so what we're going to do is talk about sampling and sample distributions. This ties directly back to the distribution curve, because now what we've previously talked about is that you've worked with a population. You've known the overall population statistics. You've known the mean, the mu, the mode, the median, the standard deviation, the sigma, everything that goes into a population. But now the principle here is that if you have an infinite population or a large population, what do you do? Or there might be situations where you have a destructive sort of environment that, in order to figure out, as an example, the safety of a vehicle. We've talked about this before. If you want to find out how safe your vehicles are, and if you took every car that came off the production line and ran it into a brick wall to find out how safe it was, how safe the vehicle was, what would be your sales for that month? They would be 0, other than maybe some scrap. That's it. So the point being here, that's a little bit of an extreme example, but it's not necessary, because you can take samples, and this is what all of probability is really based on from this point forward. It is based upon the fact that you can take a sample of an overall population and within some type of confidence level decide whether or not you're going to make a decision one way versus another. And you're going to hear the term P.05 for ever and ever for at least through the end of this semester, and then probably half of BANA 2. All right, and P.05 is just a P, and it's .05, and that's the way it's written. These little triangles on there now so I don't go too far. And here's what we're going to talk about. First off, it's going to be selecting a sample. How do you go about selecting a sample of a population to make sure you have randomness? Because if you don't have randomness in your population, you may be experiencing bias. You may be experiencing invalidity. You may not be able to repeat what you've done in your testing over and over and over again, and that's reliability. Okay? So you want to minimize invalidity, and you want to maximize your ability to repeat over and over again what the experiment that you created. Okay? And that's the reliability. Because if you get the same answer 20 times, and you've done the experiment the exact same way, it's probably a pretty good experiment, or a pretty good experimental design and methodology. And everything that we're talking about here, there are 3 methodologies, obviously. There's quantitative, which are numbers driven. There's qualitative, which is textual, okay, the feel. And then there's a combination of the 2 called mixed methods. And what we're homing in this course and BANA 2 for the most part is on the quantitative side, the numbers. We'll talk about sampling distributions, and you'll start hearing terms point estimators, where you've created, off of the sampling, you've created an estimate of the overall population. So remember X bar? Every population mean is going to have an X bar, which is the sample mean. Every sigma is going to have an S as a point estimator. And then we're going to talk about a little bit about sampling in general, and then talk about sample sizing. And there's some techniques that are out there. There's really 3 or 4 ways you can get the sample sizing. And there is a, by the way, if you want to take a look, it's a white paper that I created a few years ago. There's a white paper up on sample sizing. I'll also reference it at the end of this module. Population is everything. If you wanted to understand what all of the United States of America, including everybody from age 0 to 115, okay, and you want to sample that population, what would be the overall population for the United States of America? Just a rough number. 350 million, right? If you wanted to sample or take a view of everybody in the world on this planet, you'd be up around, what is it, 6 billion now? 7 billion. Thank you. 7 billion. Hey, by the way, your moles, Jared, your moles from last week, I looked that up. That's actually similar to the value of E. I just didn't recall that from my chemistry days. It's been a long time, so it's like E or pi. But that was a great example. All right. And kind of segueing off of Michael's thought there. Now, if I want to take an understanding of everybody in this classroom, what would be the approximate population size? 28? Something like that. All right. Now, in order to understand if everybody is in order to understand whether everybody is getting a comprehensive knowledge of statistics, do I have to go out and talk to every person in this class, or get a sample off of everybody in this class, or ask everybody in this class what is their progress toward understanding statistics? Probably not. I could go in and I could actually probably get it to the point where maybe 10 or 12, and that would probably do it. And we'll go through some of the concepts in behind that. Okay. And it's always a subset of the population. And in some respects, as they say here, it's a frame. But really what you're doing is you're saying, okay, here is the parameters that I establish around this population. And then I always choose from that population. For example, if you put 100 names, to go back to the hat analogy, if you put all 100 names into a hat, and there are 100 of them, what is the population of the names in that hat? 100. If I pull out, if I pulled out 20 of them, what would be the sample for that hat? 20. So I have a sampling of n, small n would be 20. So the framing is the parameters that you put around the population. And if you go outside the population, for example, if I all of a sudden I see a name over here, and I'm just trying to use the best metaphor I can or comparative I can, but if you go outside the hat and get someone from outside the hat that's not in the population, what have you just done? You've introduced bias and invalidity. And that's really what they mean by the term framing. And the bottom line here is that it's just not necessary. Sampling can be destructive. Why else would you want to sample? It can be destructive. Why else would you want to sample? We've already talked a little bit about this. Yeah, it could be generally not doable. All right, Michael, you had a thought.
Like the population could be too large.
Yes, exactly. Right. And the bottom line is you don't have to. in order to make a business decision. That's really what we're talking about here. We're all in the business. Most of us are in the business discipline, okay? And what you're going to have to do is you're not going to have perfect information when you're deciding whether or not to go forward with a new product. You're going to have a sample of all the potential customers out there, and you're going to have a confidence level or a confidence of probably about 95% confidence level that your market research was correct in identifying the specific features that this product needed to have. Now the problem there is there's a 5% chance you're wrong. But in order to continue to understand the market beyond just a sample, and let's say you have 10,000 customers, you're going to spend a lot of time, a lot of effort, and by the time you actually get to understanding what everybody truly thinks, 100% of the population understanding or opinion on a feature, it could be years and the market passed you by. And that's a practical sort of business application of why we use statistics. And every company has a level of risk that they're willing to take. Some people, for example, large companies, the P&Gs, the Third Fifth, or is Third, the Krogers, I'm actually a patron of theirs, the Fifth Third, Krogers. Okay, they make decisions at a very high confidence level. And however, what do you think? What level do you think an entrepreneur? What probability or risk level do you think an entrepreneur makes? Is it less than 95% confidence level? Absolutely, because if it were 95% confidence level, the big guys would be in there. What would you think? What would you estimate that an entrepreneur, somebody who's starting up a business, okay, and they've got this idea, they've got this new app, they've got this new technique, they have this new offering. What do you think they make their decisions at, as far as being right or wrong? 75, yeah, at least. It might even be lower. It might even be lower. It might be a 50-50 shot. So think about this. If you're an entrepreneur and your payout is potentially $10 million in 5 years, and you've got a 50-50 shot at making that company or making that $10 million. Now, on the other end of the spectrum, you work for a large company. They're making decisions at P.05. And as long as you mind your P's and Q's and don't torque too many people off, you're going to be a part of that 95% probability, and you're guaranteed $100,000 a year for the next 5 years. Which one are you taking? Or you're 95% guaranteed? There's still a 5% chance it's not going to work out.
So,
Which one?
I'd work for the big boys.
Work for the big boys and take the actual money.
Because I'm probably going to get insurance too. And vacation days.
Yeah, you want at 10 million. You don't have to worry about insurance.
I know, but like I could lose all that. Not get
I'm sorry.
You don't have to worry about vacation days either.
I'm sorry. You're risking it, and why? If you don't mind, just kind of give me a feel for why you would 50-50 shot to get 10 million or $100,000 a year for the next 5 years, and you'll still get benefits when you're with a startup company, by the way. Ooh. Yeah, exactly. Why do some people go to? And is there anybody else who would take that 50-50 shot on 10 million? You would. Why?
Because it's 10 million as opposed to 100,000.
Yeah. At the end of the 5 years, you got $500,000, and actually by the end of the 5 years, what do you really have in the bank?
You're probably in debt.
You might be in debt, depending upon.
$10 million in debt, or I don't know. You're probably like at least $1 million in debt.
Oh, for a startup?
If you're gonna have like a gross margin of like $10 million over 5 years.
No, you're going to have $10 million in your pocket.
Oh, in your pocket. Okay.
You walk away, you exit. You get bought out. Your company, and this happens every day, your company gets bought out, and you get $10 million for a 50-50 chance. Or you can take 100, and then at the end of that, 5 years, you might have some debt. You might have $500,000 in debt, all right? But now you still have $9.5 million, and if that doubles every year, by the time you're 50, it'll be worth $50 million. No, you get interest off you invest it. You're a good investor. Yeah. Yeah. Think about the people at Enron. Ever heard of Enron? Right. What was their risk level that those people were working in with inside a large? Somebody was betting the ranch, and the people that were working there didn't even know it. That was the problem at Enron. And in fact, it was so much so that people put their life savings and all their retirement into Enron stock. And they didn't know what risk level they were at. They were probably at about, they were probably rolling 75%. It wasn't quite entrepreneurial. But if you have a 50-50 shot, if I have a 50-50 shot, I am 22 years old, 23 years old, I'm in. What's the worst can happen after 5 years? You got to go find a job. Yeah, you can find another one. Yeah, or you can start up another company. Get some. Okay, so everybody has their level of risk that they're willing to take on. Okay, if you have, oh, here's another one, and then it's situational. If you have 3 kids at home, you have a mortgage payment, and the mortgage payment is $1,500 a month, and your kids have this nasty habit of eating and wearing out tennis shoes. Now, what say you?
A nasty habit of eating. Is that what you're saying?
Eating and wearing out tennis shoes. Yeah, they all eat. It's this amazing thing. And if you got guys, it's like the refrigerator gets cleared out once every 3 days. And then you find half of it downstairs and not eaten. But you can't put it back because that's the way guys are.
This is reflective.
It is reflective, absolutely. All right, so you can have, we talked about a finite population. A finite population would be similar to what we have here. We have 30 people in this class. That is a finite population. We also have an infinite population where any outcome is possible. And the number can be so large that even if it's a finite, it's still infinite, because if you're talking about 6 billion people, okay, that's an infinite, it's a finite, but it's really infinite as a matter of practicality. Here are some great examples. Organization membership. Anybody in a fraternal or an honor society? Anybody in an honor society? We get an honor society? Yeah, Austin. There are X amount of members in that honor society. Was it Alpha? What is it? What is it? Alpha Mega or something? Or?
National Society of Leadership and Success.
Excellent. Okay, and there are a finite number, and you could actually go in and create a survey, 10%, maybe 5% of those members, and get a pretty good feel for how those people feel about the National Society of Education and Leadership. I didn't even say that right, though. All right. Credit card account numbers. You can go in and they're MasterCard. How many credit card account numbers do you think MasterCard has, or Visa? Millions, tens of millions. It's finite. So you can go in, you can create actually a sample size off of those, but in some respects it's also infinite. Inventory product number, SKUs. Somebody works at a grocery store. Who works at a grocery store? Grocery store, yeah, you have SKUs, right? What do they call them, SKUs still? Or the barcodes, right? The barcodes, yeah. Okay. And from a finite population, you can pick n amount of samples. And here are some other rules or kind of general guidelines. There are tools. One of the more important things here is that from a finite population, for example, where I'm going to use the example here in a couple seconds, is that if you have 2,000 people that work in your company and your HR, and you want to randomly select, that's the key to sampling, is it has to be as random as humanly possible. And you can go in and you can create randomly generated numbers where every person, this is the key to randomness, is that every person within that company had an equal chance, or an equal probability, let's not say chance, an equal probability of being selected for this survey, for this human resources survey. And I think I got another example here. Yeah, there are 900 applications at the St. Andrew College, and they want to, or applicants for admission. Applicants were numbered one. You actually number them 1 to 900, and you want to, for whatever reason, you want to sample 30 of those. So what you do is you take each one of those and put a number to them, and then you can randomly select 30 applicants. And here are the actual steps. And so you can do this in the computer. And I think if we've got time, I'm going to at the end, I'm going to create a random sampling process, and then you'll go in and we'll do it over the lab here. And each of them is assigned a number, and each of them has a probability from 0 to 1 of being selected, equal probability. Now here's a quasi-automatic. What you can do is you can also go in and you can randomly assign a number from 0 to, for example, here 845, and 0 to 845, and then you can have a random number generator that goes in and creates what's on table 7.1, and I think I've got an excerpt of table, yeah, here it is. So if you go back to table 7.1 on page 302, you'll have all of these random numbers that have been generated. And so what you do, of those 845, here's employee number 37, 447, 748, and 189. And your random selection process is that you've selected the fourth person in each one of these columns. You don't know who they are, but they each had the exact same probability of being selected out of the 845. So 1 out of 845 to be exact. Talk about infinite population. The issue here is you cannot use a random selection on an infinite population, because the population, you would have 6 billion random numbers generated. Again, it's the practicality of it. So what you do is you'll use a random number selection procedure, but you won't actually go in and assign those to each of those individuals. So here's an example of a sampling from an infinite population. Parts being manufactured on a product line. For example, if you're Coca-Cola and you want to sample how full the cans are for Coca-Cola, because you want to fill them to exactly 12 ounces or as near to 12 ounces as possible. Because if you don't fill it to 12 ounces, what happens? If you all of a sudden you have a manufacturing process and somebody looks inside the bottle and sees that there's 10 ounces in there.
Sue them.
You would sue them, a class action, you betcha, all right? You could sue them, of course. Or, what else might you do? Yeah, you go buy Pepsi. Because Pepsi, always fills their bottles to the full 12 ounces that you were expecting. A bank, telephone calls. Oh my goodness, you have telephone calls not only arriving at a technical help desk. I mean, they do get a ton of them here. But let's talk about you want to understand what's happening in a telephone network that is making or a wireless network where there are. I mean, each of you have probably already made 3 calls this morning. How many people have made 3 calls this morning already? How many people have made 1 call this morning? How many people have made 2 calls? How many people have used their text message at least once? That's an even better one. All right. So, well, let's say you have all these text messages, and this is just in this class. I mean, it's amazing, and it's an exponential growth that's going on, and you want to understand the habits of text message users by time of day or something like that. Do you have to go in and look at all billion messages that were probably created each day on the planet? No. All right. So customers entering a store. This is kind of finite, and this is where there's a differentiation between finite and infinite. infinite is where it just becomes impractical. For example, Jared at the store that you work, where do you work again?
Best Buy.
Best Buy. There are a finite number of customers that walk in the door. Is that right?
Correct.
All right. However, there's so many customers that walk in the door every month that it might be impractical to survey all of them. So what is a finite number turns into an infinite sort of situation. Here again, the key is that random sample so that you can make, and this is why they call it inferential statistics. You are inferring something about a population based upon a sample. All right, and as long as the randomness of selection is complete and not biased, you will be able to say within some level of confidence that the decision you're making or the information you have has the ability to predict or infer something about a statement or a hypothesis or a question that you're trying to answer as a business person. And by the way, the other key piece here is there has to be that independence. And this goes to point estimation. What we do here is we refer to a point estimator as the sample mean, for example. Okay? The sample mean is a point estimator of mu, of the overall population. But just because you took a sample, you took 100 samples of an overall population of 100 million, and this was infinite, 100 million was infinite, and about 100, maybe 200, you can begin understanding that you have a certain amount of statistical power, and that's an actual term, statistical power associated with your sampling. And what you can do is you can go and say, okay, this X value, this X bar, probably within 95% confidence, and this is why you see all the time that people use in surveys, plus or minus 3%. There's a confidence level that's there. That even though you picked out an X bar, but it's of the overall population, there's still a 5% chance or some percent chance that you did not pick out or you did not calculate the actual mu for the overall population. You inferred it, but your inference was wrong. And that's called a type 1 error. You think you found something, but you didn't. And just as we have with X bar for mu, we have S for sigma. And N is the mathematical symbol for, small n is the mathematical symbol for the sample itself. And N is capital N is for the size of the population. We can also do this with proportions. Proportions are really nothing more than if you use, instead of a specific number, you use a proportion, so 30%. So what's the probability you're going to get 30% of the people pick correctly? Okay, and we'll talk about that as well. So let's go back to our friends at St. Andrews College. Here we had those 900 applicants, and you want to understand what the SAT scores were. All right, and so do you have to go, if you want to figure out what the SAT scores for all 900 applicants are, do you have to go back and find out the SAT scores for all 900 applicants? You could, but you really don't have to. Okay, and especially if you want to, especially if you don't have the information associated with the proportion of applicants that want to live on campus for those 900 applicants. All right. And here's the issue, is the information has not been entered yet. But you still have to make a business decision on how many people are going to use the dorms based upon their SAT scores as an example that we're using here. If the computer gives you 30 you're going to create a point estimator for the overall population of mu. 30 is the population of the sample, x bar, and the overall population mu is 900. All you do here is very simple. You take those estimators, or those 30 samples that you selected at random, you sum them up just like normal and divide by 30. If you want to get the standard deviation point estimator, because standard deviation is also important to you, because you want to understand how much dispersion you have within your data set, how much variance you have. So you can estimate that as well, and there's the formula there. And then you can do the same thing for a proportion. Okay? So you can say 20 out of 30 would be another way to create a point estimator on a proportion. And here, this was for these these were for the all 900 applicants. And now you've got an actual number that's 1697. And now you've got an actual standard deviation of 87.4. You have a proportion of 72, the population proportion wanting to live on campus. How close? $16.97. Your point estimator was $16.84. Close enough? Maybe yes, maybe no. Some people would say, you know what? I'm not going to do that again because I didn't get because I think that the difference between the actual parameter value of 1697 and 1684, there was too much gap there. I can't make decisions on that. But other people would go, heck, if that were even 1650, I'd still feel comfortable that I was able to pick up the population. Same way with the standard deviation, 85.2, 87.4, pretty close. Close enough for government work, as they say. And now the proportion. Here's the exact same thing you have here, as you have the proportion, 0.72, 0.67. Now that one, I would say that is pretty significant difference. Especially if you're talking bigger numbers as well. If you're talking about 3,000 students, and you 67% versus 72%, or let's call it 10,000 students, 67% versus 72%, you could be off by 500 students. That's a lot. So everybody, as Ashley and Michael and Casey said before, everybody has their level of risk at which they're willing to accept that they have the right answer that they can make a business decision on without perfect information, because you will never, ever, almost never, ever have perfect information as a business person. And that's why you see some people, you always heard the term, man, that guy couldn't make a decision to save his soul. Well, that's because the person they're not a risk taker. They want perfect information, but the problem is in business, you're not going to get perfect information. And so that's what they call paralysis by analysis, the bureaucracy. People just won't make decisions because they want to have perfect information, and the world does not exist that way. I worked for a guy, and he was the director of engineering. And that guy would actually wait for the whole rest of the company to make a decision before he would make a decision on what he probably should have made a decision on 6 months ago. And so now he says, well, I'm right. Well, of course you're right, because you waited for everybody else to make a decision, and now you have the information that shows you're right. So why do we need you? So what I want you to do is take 711A on page 308. And I didn't mean to put the fire hose to you, but this is the sort of thing that there's a lot of base information that needs to be pulled together, and then you can start doing your exercises. And we'll do more. I've actually got a number of these set up. So that 30-minute block of instruction was about as brutal as it's going to get. Let's take this to we're going to take this to a whole new level, and this is why this is such an important concept. as long as you create a targeted population, as long as you put parameters, a frame around that population, and you don't accidentally, for example, go in and say, well, I'm more interested in iPhones, but hey, you know, if a couple of Blackberries get in there, no big deal. Well, that is a big deal, especially if a large number of the samples are from the Blackberry. Then you're trying to evaluate the iPhones as far as what their success rate is going to be. And you have to take the sampling itself from the population that you're interested in testing, or the situation that you're interested in testing or finding more about, or hypothesizing. We'll start creating hypotheses. Hypothesis is nothing more than your best educated guess. Okay, that's a little bit of a Schulteism, by the way, educated guess of what is the actual mean. And we're going to infer from that population of 5, in the example that you went through, the population of 5, you're going to infer about the overall population that the mean of the population, mu, is 9, with some level of confidence. And here's the process. It populates all by itself here. Good. Good. So you have this population over here, and you have this mean, but you don't know what the mean is, or it's impractical to find out what the mean is. You've got too many applicants, too many people, too many parts, too many of this, too many of that, and it's just an infinite sort of population. And so you say, well, you know what? I don't have to spend all this time and all this effort to go out and find out what everybody in that population is thinking, or what every part that's coming off the production line, or every soda can that's coming off. Do we call it soda or pop here? Pop. Every pop can that's coming off of the Coca-Cola line. Okay. And so what we do is we create a value of x, and we infer about mu, and you will actually put in the value of x bar into here as the expected value, with some level of probability that you're wrong and some probability that you're right. And that's why we say the expected value of x is actually mu. So to be more fair here, if I had said the expected value of x is equal to 9, now if I put that up and I gave you no other parameters, you'd be able to say mu is 9. But there's a chance you're wrong. There's a pretty good chance you're right, though, assuming that you've done your methodology and everything else correct. And the point estimator said to be unbiased. If you go in, you create the proper parameters, you go in, you select only from that parameter or that population that you created this fence around, then you're going to come up with a pretty good point estimator for the population. And we can do the same thing for standard deviation. And here are the different areas that you want. Here's the standard deviation of x bar of the sample itself. You'll use these a couple of these to create there's a mathematical formula, and I'll show you what that is, on what is the standard deviation for x bar. And keep in mind that n is a sample, and small n is a sample, and a large N is the population. Sigma is the standard deviation of the population. And this is the notion here where you have a subscript on x bar. That's the standard deviation of the mean, or the distribution for the mean. Here's how you calculate these guys. If you have a finite population, if you're only dealing with the 28 people in this classroom, if you know the n and what your sample size is, and you know what the standard deviation is, you know what the standard deviation is for the population, you can get the standard deviation for the sample, the distribution itself. For an infinite, here's the formula. Just take the standard deviation of the population over the square root of your sample. Now everybody says, well, that's easy enough. However, there's a whole other piece in here that comes into play, is that what if you don't know the mean of the population, what's the likelihood that you're going to know the standard deviation of the population? And then you've got another hurdle that you have to overcome with a statistical method. And here, by the way, the Cygnus sub x, you'll also see this referred to as standard error of the mean. And you're making an approximation of the mean for the overall population based upon a sample size of 30. Now, the key here, and this is why we've talked about normalcy so much. Okay, we talked about normalcy. If you don't have normalcy of distribution, you can't do a comparison of the means or a Z and T test. You have to go find another test. So in this class, we're always going to assume normalcy of distribution. And normalcy of distribution just means there aren't so many outliers that you pick up skewing. Remember how we said skewed to the left, skewed to the right? Positive skewing, negative skewing. The key is, or one of the underpinnings of being able to use what's called a parametric test, or the t-test, z-test, chi-squared, on and on and on, is that you have to have a non-skewed and a not overly pointed or peaked distribution. Now, the good news is we have this theorem called the central limit theorem. And this is helpful in understanding, and the central limit theorem builds off of the normal distribution curve that we've talked about before. And you select if you have a population of capital N and you're going to pick N samples, you can say that eventually, as you select more samples, you're going to come closer and closer to the overall population mean. Case in point. All right, if you have 100,000 people in a population, and you just keep sampling and sampling and sampling, and finally you get to 99,999. What's your confidence level that you have gotten to the correct mean for the population using a sample size of 99,999? Yeah, it's almost an absolute. And that's what the central limit theorem is all about, is that eventually, if you get high enough into the sample size, you will find the population mean, or the actual estimated point for this, and it can apply to the standard deviation, it can apply to mean, it can apply to variance, and on and on. So here are these SAT scores again. And you can see here, this is the normal distribution. As we've talked, here was the 1697. The expected value of x was actually x bar, and which is mu now. Here's a standard deviation. And so what I want you to do is, for a normally distributed infinite population that has a mean of 75 and a standard deviation of 5, you pull out a sample of 40. What are the answers to those questions? here this time. Over here by our friend Jarrett. There we go. Oh, where's my little pointer? All right. So here, let's go back to the St. Andrew College example again, and we're going to expand on this even more. Now we're going to say, okay, what's the probability that you're going to get a range of values? And the range of values here is that you're saying, okay, you have this SAT score that is within plus or minus 10 points of the actual mean. You've determined that, you know what, I'm only going to use this study if it's plus or minus 10 points on an SAT. What's a good SAT score? No, that's ACT. SAT? Oh, 1100 might be a pretty decent score. Is it pretty low? What would be a good one? 1400 would be outstanding, yes. 1400 would be outstanding. So 1687 and up in here, this is a really nice college, or really selective school. And so what you're saying is between 1687 and 1707, as long as I'm going to pick up those values there, I feel comfortable that my study, when I do it in the future, is going to accurately project whatever I'm looking for again in the future, next year. And you've created this methodology. As long as you follow the same methodology next year that you did last year, you're going to get a plus or minus 10. Or in this case, a plus or minus, well, you're actually within 10 would be 1687, would be, you're pretty tight here. This is within less than 1%. So you're going to be calculating this about 99% confidence interval. What you do, you can pull out your handy dandy Z table again. And you get your upper point probability. And the way you do that, you just go x minus mu. Okay. The actual point that you're interested in, or actually this is x bar at this point, but it's really mu is because it's an expected value, and divided by the standard deviation. And that's a 0.63. So z is equal to 0.63. You go into your text in the back of your book, or onto a chart that I'll give you on the exam if you want to be exam specific. What would be the probability when z is 0.63? That it's going to be, this is the upper end point, so it's going to be lower, less than. There you go. Then you're going to look at the under the curve to the left, 0.7357. So that's the upper point. So what you have now is you have the number, you had mu, which was, what we say, was 16, we said the expected value was what, 1697? Isn't that right? And then we had 1707 on this side. And so what you're doing here is you're looking for that area under that curve, just like we did previously. No difference. The only difference here is we're starting to put this into a practical setting, because it would be good to know what the average ACT scores are going to be before they're loaded. So you can start saying, well, what kind of faculty do I need? I mean, clearly you need a different faculty if you're doing a 1200 versus a 1600. Okay, sort of approach, potentially. Here's where you went in, 0.7357. You went on the table, 0.6, Z, 0.6, and you're on the positive side, 0.63, 0.7357. And there it is, 1707. And so this area under this curve, or this density as we've talked before from the table, is 73%. So that means 73% of all the numbers, or all the ACT scores or SAT scores in this situation, are going to be less than 1707. It also means, conversely, keep this in mind, is that there is about, what, 27% chance it's going to be greater than 1707. And we go to the lower end, a minus 0.63. How convenient. And now you're at 26.43. So now you would look on your negative table, on your negative z table. And here's the way this is going to look. And keep in mind that when you're on the negative, you're going to the left. Oh, here's an interesting point here as well. Since we're working with x bars, you'll see that these tails are asymptotic, meaning that they don't touch. Because what if they touch? You've just picked off the whole population. So there's no reason to talk about samples. All right. So do this one and figure that one out. We'll use the same numbers we had before. Maybe this will help. Let me go back and grab those formulas.